Okay, I'm András Kovács from University of Gothenburg and Chalmers University of Technology. And hello everyone. I would like to talk about Eta-conversion for the unit type, which is still not that simple even after this talk. So, what is the problem? You can see here this rule for the unit type, which really just says that if you have two terms of the type, then they are convertible. And there are no other conditions. You can just take any term whatsoever and any other term, and they will be convertible. And then one issue with this is that so because they really can be any terms, they can also be distinct bound variables. And another problem is that if we also have eta rules for pi types or sigma types, then we automatically get many more types which are definitionally uniquely inhabited. For example, you can take any function type which iterators in unit, and it's also going to be definitionally irrelevant because every inhabitant is just equal to some lambda, some constant lambda returning the element of the unit type. And you can also take products of irrelevant types, and they are also going to be definitionally irrelevant. So this means that conversion checking has to compute some types. And but there's one question: is if this is so complicated, then why do we even want to have unit eta? And I would say that in many situations, unit eta is not essential, but it is nice to have. And another thing is that if you have a good implementation for unit eta, then it can be reused more generally for other features, which also imply some definitional irrelevance. For example, singleton types, extension types in cubical type theories, and also the implementation of strict propositions. So what about unit eta in current implementations? In ROC and Idris 2, there is really no attempt at supporting it. There's just a purely syntax-directed conversion, and that's it. In Lean 4, so the story about Lean 4, I looked at it 2 days ago. So if you just write down this definition of an eta rule for the unit time, it works fine. But if you write down a slightly different eta rule for the functions going from unit to unit, then this is rejected. Yeah, so this is rejected, and this is a known issue. But you can see that it's not a fully robust implementation. And then the actual kernel implementation of this is also not so nice because it works by calling an infer function on terms to get their types and check if the types are unit. So the conversion checking is trying different strategies to convert terms. And if all of these strategies fail, then in the very end, we are calling essentially an infer function to recompute the types of the sides and then check if they are unit. And of course, this is not very efficient because this infer function is doing an arbitrary computation on these terms to kind of pull out the types from them. And in Agda, we have type-directed conversion, which is pretty good in terms of completeness of conversion checking, but not quite complete. And it is also fairly inefficient because it always computes types, even if they don't really make a difference. So in this talk, I will talk about a very simple setup at first, which is just bidirectional elaboration without any meta variables. And I have lots of code examples, and we will see how many of those I can actually explain. And in the second part of the talk, I will briefly talk about what happens if we add meta variables in the mix. And as usual, it's not going to be simple, so I just give a brief overview and no coding examples. And this whole thing is partially implemented, but I haven't yet benchmarked. And so this is not really the final word on anything. It's more like just my experience looking at different designs and just seeing which one feels nice and which one feels kind of sensible. Okay, so the very basic setup comes from Thierry Cocon from 1996, an algorithm for type checking dependent types. which is essentially making a distinction of terms and runtime values. And this can be understood as an interleaving of elaboration and normalization by evaluation. And I strongly believe that this is a very nice nice approach to elaboration in general. And it also has excellent performance and also very good ergonomics in terms of the implementation. So on the left, you can see a definition of terms, which is this small inductive type for some type theory, which has variables, pi types, lambdas, applications, U for universe, and then the unit time. And on the right-hand side, you can see neutral values, which are just variables or applications of neutrals to values. And then values themselves have a very similar structure to terms, except that there is an explicit embedding of neutrals into values on one hand, and on the other hand, all the binders are replaced by actual closures or actual functions in the meta theory. And then this will enable us to do beta reductions in a nice and efficient way by just reusing the function applications from the meta language. Okay, and so what is the extension that we want to make? So we add lazy types as an annotation. So I'm using this lazy here in kind of an informal way. So I'm just assumed that this is some kind of strict functional language, some kind of pseudocode for a strict language, and I'm explicitly annotating what I want to be lazy. So I put this lazy type annotation on neutrals, and this is really just a type of the neutral. And then, so how do I compute? Okay, so let's continue a bit more with the explanation of this setup. So what are the functions that I need? I need an evaluation function, which evaluates terms into values. I need a conversion checking function, which compares two values in a recursive fashion and then throws some exception if they are not actually convertible. And then I also have the two directions of bidirectional elaboration. Inference returns some term alongside with its type, and then checking takes a type as an argument and returns a term. And then let's look at, so what happens in evaluation if I have these type annotations on neutral values. So this up function, as you can see, which goes from values to values to values, is kind of the semantic implementation of application. And so if on the left-hand side you have a neutral value, then we create a new neutral value on the right-hand side. And we also compute using this type of up function, the type of this application. And it's not very surprising what it is doing. It just picks out kind of the binding from a pi type and just applies it to a value. So this is just an instantiation of the codomain type of a pi. And it's important that we do this computation lazily. So this is just a thunk, and we don't really compute anything until we actually look at this type. And then you can see that in evaluation, if I have an application on the left-hand side, I just call the semantic equivalent, like the semantic correspondent of application on these evaluated terms. Okay, and then to finish up this version, I have conversion checking, and I have a function which tells me if some type is irrelevant. And irrelevant in the sense that all inhabitants of the type are definitionally equal. The type is irrelevant if it's a unit type, or it's irrelevant if it's a pi type, and then when I instantiate the codomain with a fresh variable, it is also irrelevant. And any other type is not irrelevant. So in conversion checking, now I can look at the case when I have two neutral values. And so what I do is that I try to convert the neutral values on the two sides. And if that doesn't work because I get some exception, then I can test the irrelevance of the type. And in this case, because I'm assuming basically homogeneously typed conversion checking, I can just randomly choose to look at the type of the left-hand side or the type of the right-hand side, because just by assumption, they are definitionally equal. So how does this work, and why is it maybe not so bad? So one thing which I like is that conversion is still syntax directed, and essentially the whole look and feel of conversion and elaboration is still very much syntax directed. And really the only place where we have to even care about types is just evaluation of applications, and then in conversion checking this single case when we are looking at the neutral values. And because of the laziness, this means that types are only computed if conversion checking depends on unit eta. So we usually, by default, we assume that things are actually definitionally relevant. And if we get into if we throw some error, but then later we learn that this is not actually an error because of some irrelevance of some neutral, then types are computed. But otherwise, types are not computed. So if you have some program which doesn't actually rely on the unit eta, then types are never going to be computed. But in the case that types are computed, then they are computed reasonably efficiently. So, and let's look at an enhancement of this setup. And this is kind of a pretty obvious optimization on the previous version, because if you think about it, the elaborator, so the bidirectional elaborator, already computes many types, because part of type checking is to do conversion checking on some expected types and some inferred types. So whenever that happens, because types are computed anyway, we can also compute relevances of types at the same time. But let's start from the beginning, and let's look at what kind of modifications we need to make on the previously seen functions. So first, for values, we add another annotation. Now this is a maybe bool annotation. And this means that, so just true means that the type is irrelevant, just false means that it's relevant, and nothing is that we don't get any extra info, because this maybe bool is some extra info which we really only get from the elaborator, and we don't get it from evaluation or from anywhere else. And then what about the implementation of application? So if we have a neutral case, so if we have a neutral value on the left-hand side, then we need to update the irrelevance of the output. And the rule here is simply that if we know that something is irrelevant, then like if we have an irrelevant function type, then applying it to anything is still going to be irrelevant. And in general, in Martin-Lev type theory, if you have an irrelevant thing, then you can never extract by computation any relevant thing from it. So all the eliminators of the irrelevant types can only return irrelevant values as well. And in every other situation, we just don't know anything about this extra annotation, so we just put there some nothing. And then we have this conf type function, which is a specialization of conversion just for types. And what it does is that it doesn't return some unit, and with some possibility of exceptions, it returns a maybe bool, exactly the same kind of maybe bool that we've seen before. And you can see here that I do the usual structural recursion on values, but in each case, I just return as a return value this computed relevance. And this is basically no extra overhead on the top of ordinary conversion checking for types. And I also extend terms with an extra constructor for annotations, like these relevance annotations. So the general idea is that in type checking, I do some conversion checking, I learn some relevance, and if I do learn something about the relevances, I just put it into terms. And then when I evaluate those terms, I can plug in these irrelevances in the neutral values that I get from evaluation. And kind of the final piece in this is conversion checking of neutral terms. And now I have some extra information about irrelevancies of the two sides. And you can see here that first I can just test if I know that that these neutrals are irrelevant from the information that I get from elaboration. In that case, I do not have to compute anything. I immediately know that the sides are convertible. And otherwise, I do a conversion checking of these neutrals. And if the conversion checking fails, potentially I still have to compute the relevance of the type. But that relevance computation can be also potentially shortcut by the same information that I get from elaboration. So this is kind of the general scheme. And then this can be enhanced a bit more, but I think that these enhancements are potentially too clever and too fancy. So one enhancement is that we might also want to memorize the relevances computed during conversion. So we have seen previously, like for example, this is irrelevant is a function that we call on types, and potentially we also want to memorize all the results of these is irrelevant function calls. So this is one potential optimization, and for various reasons it would be a bit annoying to actually implement in an elaborator, but it's perfectly doable. Another optimization is that we don't just return a nothing from conf tie if, for example, we hit some neutral type, but we could return some representation of a blocked computation of a relevance. And then one example for this, so let's imagine that you have a potentially very big record type where all the fields are irrelevant, except that there is just one field which has a neutral type. And if we go back a little bit, so we do this conf tie. So if we are doing a conversion checking on such a big record type, conversion checking, like testing it against itself, then we would get nothing as an output of like nothing as an information about the relevance of the type, because it has just one field which is neutral. But then this partial information, like this partial computation that we do when we compute these relevances, could be also represented in some way and could be also returned from this conversion checking. But anyway, so all of these fancy enhancements should be benchmarked, because it could be the case that they are pointless in practice. And let's talk just shortly about what happens if we add meta variables into the mix. There are many complications, and most of the Agda issues relating to UniTheta are really about the interaction of meta variables and unification and UniTheta. So essentially, this is where the incompleteness of Agda comes from. And but probably I want to skip this Agda example and just talk about what has to be done if we want to have UniTheta together with unification. So the first task is to detect irrelevant unification contexts. What do we mean by this? So let's assume some bound variables f and g, and then let's look at this unification problem of fg alpha being unified with fgt. And but now this situation depends on the types of f and g, because either f's or g's return type is irrelevant. Then in that case, we cannot uniquely solve this alpha meta variable to t, because the whole problem could be just replaced by just one invocation of the irrelevance of some type. So if we do produce a solution of alpha to t, then that would not be a unique solution, because in some other part of our program, we could potentially solve alpha to a different solution. So what we need to do is that during unification, if any enclosing neutral has an irrelevant type, then kind of if we have any error, like if we have any rigid mismatch of values, or if we if we have any failure of conversion in such a context, then we just have to bubble up to the innermost neutral with an irrelevant type and just convert the failure into a success, because actually the error occurred in an irrelevant context. And then similarly, we cannot really solve meta variables in such irrelevant contexts because they would not be unique solutions. So then attempting to solve a meta variables in irrelevant context, again, should throw some exception, which then bubbles up and then gets caught at the irrelevant neutral. And then the second thing is to detect the contractible context in meta solution candidates. So again, let's assume some bound variables f and g, and I want to solve this alpha equals fg alpha. And normally, without the unit eta, this would be an occurs error. So this is the infamous infinite type error that we often get from GHC. But if we have unit eta, it is not necessarily an error, because if this alpha occurs in a contractible subterm, we can just replace that subterm with the inhabitant of the contractible type. And by contractible, I mean that some type has a unique inhabitant up to definitional equality. And you can see, for example, that this might be a solution for this unification problem. So again, really the task is to, like when we do this right-hand side processing in the meta-variable solution, we have to catch errors, and we have to throw some errors, but then catch them contractible in closing neutrals. And then the third task is, again, to detect irrelevance, but now in a higher order pattern checking situation. So you can see this equation for alpha xx equals x. And then normally this has two solutions. And there is no reason to pick one solution or the other. So in Agda, and I think also in Koch and Dean, there would be some kind of error or some kind of warning or some kind of postponement of this unification problem altogether until we learn more information. But if the type of x is irrelevant, then the two solutions are definitionally equal. So we can just arbitrarily pick one of them, and we have a successful solution. So to summarize, my proposal is to compute types only on demand, but efficiently. And for this, it's kind of an important basic setup that we use Kokon's algorithm and like the basic setup of interleaving normalization by evaluation with elaboration. And the second thing is to kind of piggyback the relevance computation on conversion checking in elaboration, which is a cost that is being paid regardless of what we do with unit eta, so we can just exploit that computation that already happens. And then finally, systematically catching errors and converting them to successes based on the relevance of computational context. And thank you. Maybe we have time for some questions.
So in your conversion algorithm, when you have something that potentially has an irrelevant type, first you check whether they're convertible, and then you look to see if the type is irrelevant. But maybe there's some situations where it's quick to find out the type and long to tell whether something is convertible, and it might be faster to do it the other way around.
Yes, so that indeed might be the case. And but if we are talking, so the point is that we have some freedom how to structure this conversion of neutrals. And if we only have unit eta, then I believe that in practice, like depending on unit eta is not so common. So in this situation, it's probably a good idea to only look at types if we fail, because depending on unit eta is not very common. But for example, if we are depending on strict propositions, then we also have definitional irrelevance. And in that situation, it might be more beneficial to first look at the relevance of some type and then try to do the conversion checking, because we might expect that they depend on strict propositions more heavily. But this is very heuristic, so I cannot say like very concrete things about which one is better. But the point is that if we have this setup, and if we also have the extra information coming from the elaborator, then we have choices how to do this.
Okay, let's see if I remember that correctly. I believe you extended the core term type with the new irrelevance information. Is that correct?
Yes.
Okay.
I did it.
Yeah.
Here.
Yeah. So when I see an extension like that, I'm thinking, oh, could that maybe negatively affect the memory overhead of the entire system, because this is the one type that in the end makes out most of the memory, right? Do you think that's a concern, or how often will we create that?
I really do not think that this is a concern. So adding basically, if I wrap a lot of subterms in a single like relevance constructor which only has a bool annotation, that's very, very tame compared to what happens if you look at like what happens if you serialize modules in Agda or Coq or pretty much in any other proof assistant. So it's I think it's fine.
Yeah.
So.
Okay. Other questions? Oh, we are already on time. So let's thank the speaker again.